Hello, welcome back. And today I bring Pato from Pocoyo. He's asking you a question. What number has its square root equals twice its cube root? Very simple question, and maybe you know how to solve it, but later we will get back to this puzzle, to this math puzzle, okay? Because today we have to work on chapter 7, rational exponents, radicals and complex numbers. Section 7.7, complex numbers. And the objective number 1 is to write square roots of negative numbers in the form b times I. Let's understand what's this. Previously, when we found the square roots of negative numbers in solving equations, we would say no real solution. That's not a real number. Remember this? That's still true. That's correct. But today we will introduce a new set of numbers. It's called imaginary numbers. They are not real numbers. They are called, this is the name, this is the real name, imaginary numbers, yes, which includes the imaginary unit I. So this letter I, the lowercase I, means the imaginary unit. The imaginary unit is the number whose square is -1. That means, very simply stating, that I is equals to the square root of -1. Every time you see an expression with this letter I, you understand this is the imaginary unit, and you can substitute it by square root of -1. A few examples. Have a look. I have letter A, square root of -25. And before you're gonna see this, and you're gonna write no solution. This no solution means you don't have solution in the set of real numbers, okay? But now we are learning how to use imaginary numbers, and we can find a solution as long as it is an imaginary number. Let's break down, because the square root of 25 we can write as square root of -1 times the square root of 25. Remember? Let's go back one step. Just go back one step. This is equals to square root of -1 times 25. Right? And we can break it down as square root of -1 times square root of 25. We know square root of 25 is equals to 5, right? So we can write this as 5 times the square root of -1. And the previous slide we learned that I is equals to square root of -1. We can substitute this square root of -1 here by the letter, the letter lowercase I. This is the answer. For example, letter A, 5 times I, the imaginary unit. Okay. Same thing you have it. You're gonna do on letter B, -1 times square root of 32, and 32. We can also break down 32 as square root of 16 times the square root of 2 times the square root of -1. Right? This is 4. This we're gonna keep as a square root of 2, and that one we learned is the imaginary unit I. So the answer is going to be 4 square root of 2I. That's the answer for letter B. We just okay, and for letter A. For letter C, now we have something slightly different, a little bit different, because you have a negative sign in front of it, but doesn't matter, -121. The square root of -131, so let's break it down. There's negative square root of 121 times the square root of -1, and this is, what's the square root of 121? 11, right? And we learned the square root of -1 we can write as I. Oops, just one. Okay, now moving on. And a few more examples now. Let's work of the multiplication or division. Okay, let's have a look on how to multiply or divide complex numbers, square root of negative numbers. And check this. We learned that the square root of -3 we can write as square root of 3 times square root of -1, right? Which is I. Times. And we learned that square root of -5 we can write as square root of 5 times square root of -1 equals I, imaginary unit. And then we can multiply square root of 3 times square root of 5, square root of 15. And I times I. We can say this is I squared. Okay, I squared. Let's say I squared. We can represent like this. But what is I squared? We know that I equals square root of -1. If we square this, I squared equals what? -1. -1. That means this is equals negative square root of 15. Okay. On the next example, letter B, square root of -135 over square root of 5. Okay. Same thing again. We learned that square root of -135 we can break it down as square root of 125 times the square root of -1, which is I, over square root of 5. Okay? And now we can combine this. We learn about the quotient property. We can put this whole thing under the same square root. Remember? Square root of 425 over 5. The whole thing multiplied by I. And this can be simplified because 125 divided by 5 is 25. And what is the square root of 25? Square root of 25, do you remember? Yes, square root of 25 is 5i. This is the answer for letter B. And now let's move on. There is a standard form to represent the complex numbers, and it can be written in the form A, and let me rewrite here, A plus BI. That means it has one of the parts, letter A, is the real number part of the complex number, and the letter B is the imaginary part of the complex number. Okay, so if b equals 0, that means you don't have a complex number at all, it's going to be just a real number. And if a equals 0, you don't have a complex number, you have just an imaginary number. And we're going to work more, and the next objective is to add or subtract complex numbers. And maybe we will understand better what means complex number. Just by reading the definition, it's hard to understand. But let's work on examples, and we're going to see what it means. Sum or difference of complex numbers if you have a plus bi. And let's write here a plus bi. This is one complex number. A and b are real numbers, right? Any real numbers. And I is the imaginary unit. You want to add, let's say this is 1, you want to add this to C plus DI. How do you do? How do you work this out? Well, you have to add the real numbers, and you have to add the imaginary numbers separately. That's how we work this out. The real numbers are the real part of the complex number. You have A and C is the real part of the complex number, so you're going to add A plus C. And what's the imaginary part of the complex number? Yes, BI and DI is the imaginary part, so you can add B plus D times I. That is how you add, how you sum complex numbers. The difference, you have to think, you apply the same line of thoughts. Check this out. You're going to subtract C plus DI, right? So it's kind of the same thing. You subtract the real part, A minus C, and you subtract the imaginary part, B minus D, and this I times I. And maybe it's hard to understand just looking at the definition, but let's apply an example and you're going to see it's simple. It's really simple. Check those examples. We have, this is one complex number, 4 plus 6i. This is another complex number, 3 minus 2i. To add, we just need to first add the real parts. 4 plus 3, 7. So we're going to have here 7 is 4 plus 3 plus, and then we're going to add or combine the imaginary parts. 6 minus 2, 6i minus 2i. That's 6 minus 2i. And just to make sure you understand, this first part here is 4 plus 3, right? You are adding the real parts. 4 plus 3 is 7. 6 minus 2 is 4 times I. That's the answer for letter A. Okay. Letter B, we're going to work with subtraction of complex numbers. So remember, we have 8 plus 2i is the first complex number, and the second complex number, we don't have the real part. It's like 0 plus 4i. So subtraction, 8 minus 0 is the real part, and the imaginary part plus, and we have 2 minus 4 times I. That means the result is 8 plus 2 minus 4, not plus, 2 minus 4 is negative 2i, and this is the answer. Okay? Moving on, and we work now on the next objective, number 3, multiply complex numbers. Let's check how to multiply. To multiply two complex numbers of the form a plus bi, we multiply as though we have binomials. We are working with binomials. Then we use the relationship I squared equals -1 to simplify. With binomials, I remember we have a few methods. So let's find the example. Let's check the example. And the first one, we don't have actually a complex number, just imaginary numbers here, because to have the complex number, we need to have the real part and the imaginary part together. So these are, you can say the real part is 0. So 8i times 7i is 8 times 7 times I squared. What's 8 times 7? 56, right? 56 I squared. That's it? No, because you have to simplify I squared. What is I squared? If I equals, just to remind you, if I equals the square root of -1, I squared equals -1. Yes. So the answer that we're looking for is equals -56. because I squared equals to negative 1. That's the answer, negative 56. Okay? Moving on, and now you have to multiply, on the next example, multiply 5i times 4 minus 7i. And we have just an imaginary number and multiplied by a complex number. We will apply distributive property, okay? Distributive property. And then this is equals 4 times 5i, negative, positive with negative, negative, 5 times, let me just write this, 7i times 5i. I'm going to do step by step so you understand. 4 times 5 is 20, 20i, minus negative 7 times 5, negative 35, and I times I squared. Again, I squared equals to negative 1. That means this is 20i, negative with negative, positive plus 35. And we usually write first the real part of the complex number, and after the imaginary part, like that. 35 plus 20i is the right answer. Okay, let me just highlight the answer. And now let's work with complex number, with the both parts, the real part and the imaginary part, times another complex number with both the real part and imaginary parts. So let's work at this example, and we need to apply distributive property, right? And a good method to remember how to apply distributive property correctly is the FOIL method. I don't know if you remember, maybe you have seen this in high school. FOIL method. The first ones, multiply the first ones. So first is 6 and 7, 6 times 7. Now the outer ones, 6 times 4i. And then the inner ones, negative 3i times 7. And finally the last ones, negative 3i times 4i. Right? And 6 times 7, 42, plus 6 times 4, 24i, and then you're going to have here negative 3 times 7, negative 21i, and finally negative 3 times 4, negative 12, but we have I times I squared. What is I squared? Negative 1, right? So negative with negative, positive. Cool? Combine like terms. We have the real numbers are 42 and 12, so we can combine and find 54. And the imaginary numbers. We have 24i minus 21i is positive 3i. This is the result, the final answer, 54 plus 3i. Now, objective number 4, how to divide complex numbers. In the previous chapter, when trying to rationalize the denominator of a rational expression, we used the conjugate. Remember the conjugate? Similarly, to divide the complex number, we need to use the complex conjugate. It's the same thinking. The complex numbers a plus bi and a minus bi are called the complex conjugates of each other. And let's check how to apply it to an example. Remember when we use the conjugate before to simplify, to rationalize the numerator. Remember this? So we will multiply by 1 is a fraction that's going to be made by the conjugate of the denominator. 4 plus 3i, 4 plus 3i. Because the denominator, we will apply the formula, difference of perfect squares. Is a squared minus b squared. So a, just for you to remember, this is going to be a, this is b, and the formula is, let me write here on the top, difference of perfect squares, a minus b times a plus b equals to what? A squared minus b squared. This is formula difference of perfect squares. So that's the one we will apply. We will write here a squared minus b squared is 3i squared. Okay? And on the top, you will multiply. You can use the FOIL methods. You have to apply distributive property. Okay, apply distributive property, and a good way so you can do this properly is to apply the FOIL method. This is something we learned on high school. First, 6 times 4. Alter 6 times 3i. 6 times 3i. Inner 2i times 4. Times 4. And last 2i times 3i. Yeah, okay. Simplifying this whole thing, then we will have 6 times 4, 24, 6 times 3, 18i, and then 4 times 2, 8i, and 2i times 3i, 2 times 3, 6, I times I, -1, so -6. Cool? On the bottom, we have 16 minus 3i times 3i is 9i squared. 9i squared. And I squared is -1. So this is going to be -9, negative with negative, positive. Can you see this? 3i, 3 squared is 9, I squared is -1. So we have -9 here inside, -9, negative with negative, +9. Okay? Let me write this down so you don't forget. This is -9, the result of 3i squared, -9, and then we have +9. All right. 24, combine like terms, 24 minus 6, 18, right? And positive 18i plus 8i is 26i. And at the bottom we have 16 plus 9, 25. This is the answer. You can write the answer like this, or you can write like that. 18 over 25. This is the real part plus 26i over 25. This is the imaginary part of the answer. Cool. Let's move to the next example, and also another division. Now we are dividing 5 over 6i. This is a fraction. A fraction is a division. So we have 5 over 6i. We need to multiply it by 1. And we can multiply by the conjugates. But here, since we don't have the binomial, we don't have the real and imaginary, we can multiply both the numerator and denominator by the root that is on the denominator, and you remember I equals square root of -1, right? This is the root, so you can multiply by I over I. I think it's the simplest way. If you multiply by I over I, this is a 1, and we will be able to find the answer. So we have on the numerator 5i, on the denominator 6i squared. And 6i squared is 6 times -1, right? So -5i over 6. That's the answer. That's the answer. Let me repeat here, -5 over 6i. Or you can write like this as well. Okay, moving. The next objective, number 5, raise I to powers. And we need to look at it and identify the patterns, okay? So you're going to be able to understand. As long as you understand, you can see, you can identify the patterns. We learned that I is equals to square root of -1, okay? And we found out that I squared is -1. Now multiply, if you want to do yourself, you can multiply -1 is y squared by I, and then you're gonna find I cubed. I cubed is -I, and I to the 4th is going to be, you can calculate by multiplying I squared by times I squared is equals to 1. So we have this sequence, square root of -1, -1, -I, 1, and this is just I. Let me write down this. This is I, right? So this is the sequence. I, -1, -1, -I, 1. Again, if you go to I, the next step, I to the power of 5, you're going to calculate, you're going to find I again, see, I, and if you calculate I to the power of 6 is -1, again, if you calculate I to the power of 7, -I, again, and I to the power of 8, 1. You see, this is a pattern, it repeats. It repeats over and over and over. I, -1, -I, 1. So let's try to work a little bit more on this pattern and try to understand it, okay? So if you have I exponent n, if n equals 1, then you have, this is going to be I1, right? And this is I. If n equals 2, you have I2, and this is equals to -1, okay? If n equals 3, then you have I cubed, which is -I, and let me just fix this, -I. If n equals 4, then you have I to the 4th, and this is 1. See the pattern? I, -1, -I, and 1. Well, let me tell you something. If n equals 5, the answer is going to be this, I. If n equals 6, -1, n equals 7, the answer is -I. And n equals 8, 1. And if we repeat, this is going on and on and on, and for n equals 9, here, I, for n equals 10, negative 1. You can keep doing this on and on for n equals 11, negative I, for n equals 12, 1. Keep going. Now n equals 13, I. Well, we can go over and over and keep going, and this is for you to understand that there's a pattern. You repeat each four times, right? At 4 steps, it repeats itself. If you have the exponent, a multiple of 4, like n equals 4, n equals 12, n equals 16, any number that's multiple of 4, you're going to have the answer as equals to 1. So just divide the exponent by 4 and break down into 2 exponents. You're going to find the answer as long as you understand this pattern. Let's check the example. I exponent 53, okay? Now let's work here on the side by dividing exponents. 53 divided by 4 is going to be what? 3 and 1, okay? Negative 52, and you're going to have the remainder 1. So we can break it down. I exponent 53 as equals to I exponent 52 times I exponent 1, right? And we remember this. If the exponent is a multiple of 4, it's going to be equals to 1. So I exponent 52 is 1. And I 1 is just I. The answer is I. Okay? Now, the answer here is I. Letter B. Let's work on letter B. Now we have 1 over, you have a negative exponent. You can represent like this, right? 1 over I exponent 17. Doesn't look nice. Let me do it again. I exponent 17. This is going to be equal 1 over and 17. Let's work this on the side. 17 divided by 4 is going to be 4. 4 times 4 is 16, and the remainder is 1 as well. So we can represent as 1 over I exponent 17 times I exponent 1. And this is equals 1, not 17, sorry, 16. I exponent 16. the multiple of 4. And this is going to be I exponent 16 is 1. And I exponent 1 is just I. This is equals to 1 over I. And we can simplify, remember. 1 over I. Multiply both the numerator and denominator by I. And we have I over I squared, and I squared is negative 1, negative I is the answer. And I know this is a new thing. This imaginary number is something that maybe you've never seen before. Maybe it looks a little bit confusing and a little bit complicated at the very beginning, but after you practice a little bit with that, you're gonna see it's not too hard. It's just a matter of understanding that this I is the imaginary unit. The imaginary unit is equals to the square root of negative 1, and we can find a pattern. We can find answers if you have exponents, as long as you identify the pattern and do this process here to calculate the answer. Okay, this is the end of section 7.7. Now let's try to solve our math puzzle. What number has its square root equals to its cube root? And let me see, this is not going to be too hard, but you just need to be careful here because the square root, and let's say the number is x, right? We don't know the number x, and the square root of the number, square root of x, equals what? Equals twice its cube root. Twice the cube root. How would you solve something like that? And we will apply, let's simplify the square roots and cube roots, applying power of 6 on both sides, okay? And this will simplify. We will have x cubed equals, and to the power of 6 is 64, and the cube root of x to the power of 6 is x squared. Now I can divide both sides by x squared, and I'm going to find the answer. Yes, divide both sides by x squared, then x equals 64. 64 is the right answer. 64 is the number we are looking. That which has the square root equals twice its cube root. Thank you for watching the video today and for joining this section, and hope to see you soon on the next section of our course.